Welcome. This is the next lecture where we are going to show you how to use a LeNet for your color images, and the difference where it comes down from a standard LeNet as in for MNIST classification is that over there they were all grayscale images of 32 cross 32 and you were processing out. Now we are going to use another new data set which is called as CIFAR, and on over here though your spatial span of the images are still restricted to 32 cross 32, but they are all color images. So, your input is no more one single channel, but it is 3 channels of input which comes down to you. So, that is where it will have to modify, because your network cannot anymore be just taking down one single channel input over there, and the data complexity and the total number of tunable parameters will also be changing. So, as we go through it, I will get down more and more into it. So, the first part is the same on just trying to write down your header and your initial files which have to be called down, and then the next part is subsequently to get your data loaded. Now, what we do is we try to stick down to a similar kind of a conformal thing as we had in our MNIST classification problems with LeNet, and that was to take down just 100 images on my batch and then subsequently do it. So, here also I am trying to stick down to the same batch size of 100 images. My training set is trying to load it down from the inbuilt torch datasets folder, which also supports CIFAR. Now, CIFAR is basically natural images available and of small, say there are cats, dogs, animals, bicycles kind of thing, and there are 10 categories, and that is why it is also called as CIFAR 10. Now, you can just load down the data set using the same train set and train loader function over there, and this will just download if it is not already downloaded, and then do it. So, this is quite similar to using any of the standard data sets as we had been using for MNIST as well in the earlier examples. So, let us load this pipe. So it just sees that files are already present, and then they are verified and it is okay. So, my 2 trainers are created over here. Now, the next part over here is to get down and actually print down the number of samples. So, I just print it down, and quite on the different side is that while on MNIST you had 60,000 examples for your training, here we just have 50,000 examples for training and then 10,000 examples for the testing over here. So, it is that's the only difference which comes down, but other than that the next difference is obviously they are not grayscale images and these are color images, and that will make a modification to my network definition. So, let us get into the network definition over here. Okay. So, here what I do is I try to get down a convolution which takes in 3 channels on my input, okay, and then generate 6 channels on my output. So, you remember the first layer of a LeNet, and what it was doing is that my whatever was my input, it will do a 5 cross 5 convolution over there and then generate that many number of outputs, which is equal to the number of unique convolution kernels. However, over here what I have is that I have a 3 channel input over here. It is no more single channel or a grayscale image which goes into it. So, it is a color image which comes in. So, from there I am mapping it down to 6 via 6 such convolution kernels, and each of these convolution kernels has a spatial spread of 5 comma 5 or 5 cross 5, and that is what is written over here. We are not anymore explicitly specifying what is the kernel size and what is the patch, but because the first argument which goes into a conv2d operator is actually the kernel size over there. Okay. So, the stride over here still says as 1 comma 1, and then there are no paddings which are introduced over there. The next part is to do a max pooling, and the max pooling over here is to do a 2D max pooling with 2 cross 2 kernel and with a stride of 2. So, this goes down the same way as we had in the earlier case. Now, once this part is done, the next part is actually to go down and get the next convolution being defined over there. So, for the next convolution which we define over here, it's what maps down 6 channels onto 16 channels and with a kernel size of 5 cross 5. Okay. Now, that is done and then pretty much set over there. Now, the next part is basically to map down all my outputs coming down over here and then map it down to 120. Now, where we make a difference over here is just over here taking down that we are just taking in one single input coming down. Okay. Instead of one single input, you have 3 channel inputs coming down, and the rest of the network pretty much stays the same. Now, what I do inside over here is I define my forward pass, and for my forward pass what I am doing is I have my convolutional the first convolution operator written down conv1, and I do a ReLU or basically a nonlinear transfer function over there, and then a pooling operator. Now see one thing, what I have is that since I am going to use the same kind of a pool in 2 instances, it is always a 2x2 max pooling and doing it. So, I am no more defining it as 2 different pooling layers which are actually the same in their function, and I can actually do away by calling them one after the other. So, in case there were 2 different kinds of pooling operator, then maybe define 2 different pooling operators, otherwise it does not make a sense. However, for convolution we had to define 2 different convolutions because the number of input channels over there was quite different in both the cases, as well as the number of output channels are different. In case say the input output mapping and the kernel size everything is same, you can just define it once as one module, and then within the forward pass you can keep on recursively calling that module as many times as you want. So, later down in more deeper networks and more detailed networks is where we will get into reusing all of these, but the first kind of a reuse which you see over here for any kind of a functional structure, that is the pool layer which comes down. So, once I have this output coming over here, the next part is to actually flatten it out and get down a linear combination of 400 neurons coming, and that is what is connect down over here from 400 neurons onto 120 neurons. Okay, that's what I do over here as my forward pass through FC1 and then doing a nonlinear transformation as a ReLU. The next one is to do a forward pass over FC3 and then a ReLU, and then the next one is to do a forward pass over FC3, and that gives me 10 outputs over here. And since this is a classification network, as in the earlier case we had a log softmax written down, we write down the same log softmax over here. So, this is about defining the network. Let us run it, and then I have my network to be defined. So, that is what is defined as net. Okay. At this point of time, I have my network defined and all the weights initialized and available to me for further usage. So, this is quite straightforward. We did see that what I have is basically convolution which goes down over here, then a max pooling operator on the 2D side of it, and then again a convolution, and then my linear combinations coming down. And this is a very straightforward way of looking down into whatever I wanted to define in terms of writing down just single arguments coming into it is what has actually been defined on the system over there, and then there is nothing wrong. And this pool operator over here is what is being reused. So, the output which comes over here again goes through pool, and then that output is what is fed down over here, and you could pretty much do these sort of reuse of each of the modules because your forward function is how the data mapping is mapped down. It's not in the order of exactly how these things come. You can have them quite juggled up and down as well, but then the only thing which defines how the data flows is just this forward function which is where it's written. So, this was to give you a first hint for the first time that it's not necessary that all your structures will have to be written down in the same order. It's just for convenience and for easy to debug when you are trying to look into it, that all the structures as they would come down, they are written in the same order as how the network gets built up, but then that's not a necessity from the perspective of handling the data. The only necessity is that your forward function is properly defined, which can take in the data in that particular format. And then what I do is, once my network is defined, I try to just copy down my weights and keep them for my further use. So, this is in line with what we had done in the earlier lecture, where I was trying to show you that at the end of training how many of these weights have actually changed and what is the kind of a change which happens over there. Next, I check down for my availability of a GPU, and yes, my GPU is available. So, it's a great news, and then I can get started with defining it. So, since it's a classification function which I am using over here, classification problem which I am using, so my cost function or the criterion over here still stays as negative log likelihood without much of an issue. The optimizer, as in from our earlier experiences coming down, we stick down to using an ADAM or an adaptive momentum optimizer over here. So, that is what is defined, and then let us get into my training part over there. Now, the trainer does not have much of a difference coming in. We just train it over 10 iterations or 10 epochs over there. Within each epoch, what I am doing is I just load my data, and then if it's on the GPU, then I just convert it onto my GPU, and then just zero down on the gradients for the optimizer, do a feed forward over the network and get down my output. So, whatever is this batch size of the data which is over here, so my outputs are also of the same batch size, and then I find out what my loss is or what's the number of errors, wrong things which it has made down while getting classified through this network, and then do a nabla of loss or the gradient of the loss coming down over here, and finally get down to my optimizer and a step on the optimizer over there. Finally, the point is to go down as running loss, and then to get down what is the total loss which comes down over here, and then from there come down to what is the average loss during training, and then just keep on adding it down over the epochs. Okay. Now, that is great and good part. The next part is actually over within an epoch to actually look down into what is the way of how this whole thing has performed. So, in the earlier case we just had evaluated our errors or the losses using our training data, but here the point is independently over my test data set which has 10,000 examples, how does it behave. So, here what I am trying to do is in case the GPU is available, then just convert all of my inputs into a variable which is CUDA typecasted available on the GPU, then do a feed forward over the network, and then find out my predicted. And over here whichever neuron is supposed to have the highest prediction value or the highest probability is what it will throw out. Then I just find out which index over there, or that is the class which is the highest probability of being predicted out. And then from here what I do is just convert it onto a CPU number, and that is because the rest of the computations are what run on the CPU and not on the GPU. So, in case I am just I do not have an access to a GPU, so this part will not be running, and then I just run on this part, then it is not an issue because my predicted is what is already available on the CPU, and then I find out my total number of corrects, and if whatever is predicted matches down the exact class level of what was present in my testing data, then it is perfect, it is correctly predicted. So, what I do is I have down my scores given down over 10,000 examples. So, that is the total number of things which have to be classified. So, my average correct value or the accuracy is basically divided by 10,000 on my test data, and then I just keep on appending my test accuracies across all the epochs which have come down over here. So, from there going on to how to actually start plotting this loss functions over here. So, the first part is actually to look down and then try to plot down the loss, the plot of all the losses which comes down. The next part is actually to get down what is the total accuracy and then plot down the accuracies coming up as well. So, once that is done, we just look into this part which is to look down per iteration as it keeps on printing, and then finally just prints out what is the final total amount of time taken down for this to happen. So, let us get this one running. Now, once you invoke it out and then the training has started down, you see that it takes down about roughly 4 seconds to work down per epoch, and then it starts with an initial accuracy of 28%. So, that is not something which is quite convincing to most of you, because in the earlier example you saw that it itself started down with an initial accuracy of about 88%. That was, but then you need to remember one thing in mind, that that problem was rather a simpler problem, because you just had grayscale images where the background was pretty much black and the foreground in which something is written down is just in higher intensities, or like full value of 1 if you are looking down in the floating point number system. So, 0 and 1, and there is a very high amount of contrast between things, and it is just based on different strokes in my writing pattern that it is easy to discriminate. Whereas here these are small natural images. So, there are cats, dogs, apples, cars, bikes, each of small size thumbnails of size of 32 cross 32. Now, given this point that say if you have a bus which is in the size of 32 cross 32 pixels versus if you have a small minivan versus if you have a some sort of a truck given down in small thumbnail sized images, it is really, even for humans, it is a hard problem to understand. So, here it is also facing the same kind of a problem, most likely like it is just confusing around with these similar looking objects which are getting bound together. So, that is one of the reasons why you do not initially get to see that high accuracy coming down. However, one major point is that at the end of the training, when it took down 37 seconds, you can still see that there is a monotonic decrease in the loss curve as well as a monotonic increase in the accuracies coming down over here, and that makes us to one of these points that if we keep on training it down for larger number of epochs, so say put it down to train down for 100 epochs, you would pretty easily see that this goes down much above the 80% benchmark. Now, one more thing you need to keep in mind is also play down with the learning rates over there. So, change the learning rate iteratively, as we had discussed in the earlier classes of how to come down to convergences. So, after every say 10th epoch, you just reduce the learning rate by half of it and then let it keep on going down over there, and you would see that there will be a monotonic decrease and eventually it will come down to its most saturation point over there. So, once that is done, the next part is to actually look into my weights of what it was before my training and after my training. So, we make use of a similar kind of argument and objective as we had in the earlier case. The only difference over here which would come down is, in the earlier case, your first layer of weights was what is connecting a grayscale onto my number of channels, and the number of weights over there is equal to the total number of channels which comes down over here. Now, here I have an RGB image, 3 channel image coming down, because my total number of say planes on my convolution kernel is also equal to the total number of planes in my input image, or the total number of channels over there. And that is why you would be seeing down that in your first convolution kernel, in the earlier case, while you are just seeing grayscale weights, here you are going to see now color weights, because each there is a weight associated with the red channel, with the green channel, blue channel, and this is a composite visualization of each of them which comes out. There are 6 kernels in the first convolution layer, so these correspond to the 6 kernels, each is of a size of 5 cross 5, 1 2 3 4 5, 1 2 3 4 5. So, it is a 5 cross 5 which comes down over here. The next part is, this is the weight. These basically these are all the weights which are there before the training, and these are the weights which the kernel takes in after the training. And it looks more of like a chessboard, a very decorated piece of chessboard, and then nothing much to convey down. You do not see gradients or anything coming down, but then you also need to keep in mind that the network as such has not come down to a great performance. It is not even barely 50% on the accuracy side of it. However, it is doing much better than a random chance, because if you had to classify down 10 different classes, then the random chance is 1/10 or 0.1 sorry 10% is the random chance, and that would come down to an accuracy of 0.1 actually. So, instead of that, this standing at 0.45 or more than that is actually a much better performance than just a random guess. So, anyways, these weights are not yet trained, though if you look into the difference, you would see that there are gradients which are changing down. So, there are changes in the gradients in the green channel, there are changes in gradients in blue, so which is basically one of the other channels other than green which is present. Now, here do you see that there is some sort of a change in the brown shade. So, it means that there has been changes in red, green and blue, all of them taken down, and most predominantly it is basically green and red where the change is coming down. So, these look like shades of purple, which is where the differences are in the planes of blue and red. This is where it is more of like a mix of green and blue where the changes are coming down, and again you have your brown. So, going back to your basic knowledge of colors within digital image processing, you can pretty much make a impression of where which channels are getting changed over there, and you see the changes coming down in color because your images and objects on the side of in color. However, when I try to look into my second layer over there, so I am just taking down my first kernel of convolution and then try to look into all the 6 channels over there. So, I see each of my 6 channels which connect down my output of the first convolution layers and look over there. So, each is a 5 cross 5 in the same logic, and then this is just my first convolution kernel on the second one. If I look between the weights of when it is not trained versus when it is trained, there are minor amount of changes which I would see, and however, on the difference I do see that there are gradients which are sitting down over here. So, this is what comes down as we keep on moving towards color images. So, now that is as in with autoencoders, when I was explaining you for grayscale images to color images, and there was one very immense important point which was made down as that there is technically at this point of time no solution given down, or there is no definite answer of when it will converge, what kind of an architecture would come down as the best one. That's still a challenge to be solved out over here. And so, you see that in over here as well, it is the same kind of an architecture with the similar number of weights and everything which goes down. The kind of performance it has on grayscale images versus the kind of performance it has on color images is drastically different, and one of the reasons is on your grayscale images of MNIST, you had a much conformal way of representing the data. It was much easier to learn down very definitive patterns, and that is why it was able to classify them in a much better way. Whereas, if you go down to your color images, then the way in which it would be able to learn down some discriminative patterns which are of really importance and would make down sense is much low, and for that reason it takes it longer and longer to learn it out. So, if you keep on running this code over a larger number of iterations, say just change down, go up over here, and where I have my number of iterations, if you just make and change this to 100 or maybe 1000, you would be seeing that this comes down to a much conformal way of a decent amount of accuracy and a much lower loss. So that's where we come to an end with writing down very plain and simple convolutional neural networks. So stay tuned for the next ones where we start digging into deeper neural networks and why they are called as deeper neural networks and more computational complexity issues around with them. So till then, thanks and stay tuned.